Hi, my name is Nick Borson, and in this video I'm going to talk about the public and private keywords in C# and how you use them to control access to members of a class or struct. Key concepts in this video that we're going to talk about are abstraction, encapsulation, and information hiding. And hopefully by the end of this video you'll understand not just kind of the mechanics of how this works in C#, but also why, the ideas behind it, how it helps you write better programs to control access to that information. C# actually has 4 access modifiers: public, private, protected, and internal. And these can apply not only to the members of a class or struct, but also to a class itself, or to other top-level things like interfaces and delegates and so on. But for the purposes of this video, we're just going to talk about public and private, and we're only going to talk about how these are used in order to control access to members of a class or struct. All right, so like I said, key concepts in this video are abstraction, encapsulation, and information hiding. These are all concepts from object-oriented programming, which is a style of programming or a way of thinking about programming. C# and some other languages are considered object-oriented languages, or at least they are languages that support that style of programming. But orientation is not really just a set of language features. It's really a way of thinking about how to organize your program. And namely, you organize it into objects, where an object represents some sort of concept, some sort of thing in the abstract idea that you're trying to program for, and it includes both the data that represents that thing, the state that represents the state of that thing, but also the operations that you can perform on that data. And it all bundles it all up in a way that makes the object usable to people who use that object in a coherent way. So you expose certain abstractions that make sense for that kind of object. So I'll show an example in a little while of where I wrote a class, or actually a struct in C# called fraction, which represents, say, a fraction or a rational number, a ratio of 2 integers. So there's certain kinds of things that make sense for that. You would expect, if you have a fraction, that you have a numerator and a denominator. So a fraction object should have numerator and denominator properties, which should be visible to the users of the class. That's part of the abstraction. Also, you can add and you can multiply and subtract and divide fractions. So those are operations that you should perform on a fraction. And so those kinds of operations should be part of the public interface or the observable behavior. They're all part of the abstraction that we expose to the users of that class. When you use that type, when you use that object, you have access to that functionality. On the other hand, there's some details of how that works. So when you add 2 fractions, in order to do so, you have to find a common denominator so that both fractions have the same denominator, and then you can add the numerators. So there's kind of an algorithm for finding the least common denominator, and then you can add the numerators, and then you can take the result and reduce it back to its simplest form again. That kind of nitty-gritty of how that works, yeah, you could expose that to the user of the class, but it's not really necessary. They don't necessarily need that level of complexity. That doesn't really add anything to the functionality. So really, you just like to expose an add method, and that algorithm of how you add 2 fractions is really part of the underlying implementation. So you encapsulate that by making that part of how the fraction works under the hood, but you only have the useful stuff, the fact that you can add them, be part of the public abstraction. So that's called encapsulation. You're separating the internal nitty-gritty details of how it works and how it's represented from the observable behavior that your user of your class actually cares about. That's encapsulation. Information hiding is how you enforce that encapsulation. By making the internal stuff private, by making the implementation details private, it means that the user of the class can't even see it. They can't modify it. They can't depend on it. They only depend and only see the stuff that is part of what you've designed as the abstraction that they should be aware of. The abstraction should be complete enough that it does all the stuff they need to do, but it shouldn't have any extra stuff that is only needed in order to implement the under the hood stuff. The advantages of that are that the user can't bypass your your encapsulation. They can't bypass your implementation and go straight to the underlying data and potentially muck it up, right? It means that your class can protect its own integrity because its internal state is only manipulated through the methods that you provide as part of your implementation. And furthermore, it means you can change your implementation. You can change how the class is represented under the hood. And it doesn't break your users as long as they only depend on the abstractions. They don't depend on the actual implementation. In C#, we get that information hiding by taking advantage of the public and private access modifiers. So any members declared public are part of your public interface for that class, the part of the class that's visible to users of the class. So that's for the observable behavior that the class is how the class appears to people using it. The private members are just for the internal implementation. And private is the default, so anything you don't declare as public or as internal or whatever, anything where you don't specify an access modifier is private. So you can either just explicitly use the private keyword, or if you don't specify anything, then private is the default. Now, a moment ago, I talked about an object having a public interface. I just want to be clear that I'm using the word interface in a broader sense than the C# interface type. You may be aware that C# has a keyword called interface, which is for declaring types that are just pure interface with no implementation. And then you can create classes or structs that implement those interfaces. So that is one sense of interface, but there's a very broad sense of it as well. An interface is really just any kind of boundary between things through which things interact. So, even just physical objects like a car has an interface. You use the steering wheel and pedals and so on in order to drive the car. You don't necessarily need to know all the mechanics of how that car is built or constructed in order to do that. You just need to know how to use that interface, or an airplane, or whatever, or the user interface of a piece of software. The interface exposes the information you need in order to use it, and it provides the affordances that allow you to manipulate it or interact with it. And the same goes for interfaces between pieces of software. So between an object, say, and the users of that object. The object exposes properties that expose information about the object, and it exposes methods and so on that allow the users of that object to modify its state or perform whatever operations make sense for that kind of object. That is what interfaces are, and it's really just a way of making clear boundaries. It's key to writing software is to have those kind of clear boundaries because it allows you to manage complexity. If you were just writing a program that was only a few hundred lines of code, you wouldn't necessarily have to do that because it's so small that you can kind of keep the whole thing in your head at one time. But if you're writing more complex software with lots of different pieces, many moving parts, you really do have to have these kind of clear interfaces or clear boundaries, because otherwise the complexity gets out of control. You just can't keep it all in your head. So by having these kind of clear boundaries, it allows you to think about each piece on its own, and then when the piece interacts with other pieces, it's doing so through abstractions that are well defined and easy to understand, because those are what are defined by the interface. All right, so let's now take a look at an example. This is the fraction type that I mentioned earlier. I find it as a struct rather than a class. A struct in C#, the only difference between struct and class in C# is that a struct is a value type, something that's passed around by value that may be stored on the stack, as opposed to a class, which is a reference type, passed around by reference and allocated on the heap. Only difference between them. All the stuff about public and private, though, and about designing things for information hiding and encapsulation, that all applies equally whether we're talking about a struct or a class. Okay, so a fraction simply represents a ratio of two numbers, a numerator and a denominator. So we will see that the fraction has properties, integer properties called numerator and denominator. But this class is designed so that there are certain rules that it enforces. So the fraction, in order to be in a valid state, those certain conditions have to be true. These are called invariants, class invariants. So one of them is that the denominator cannot be 0, because division by 0 is undefined. A fraction with a 0 in the denominator is undefined. And second, the fraction is in kind of a standard form. So two fractions with the same value should have the same numerator and denominator because we reduce it to its simplest form. Part of that then is that we make sure the denominator is greater than 0. So if we have negative 1/3, we would always represent that as negative 1 over 3, never as 1 over negative 3. So we enforce that rule that the denominator is always greater than 0. And second, we simplify it so that, for example, we would never represent a fraction as 2/4. We would always reduce it to 1/2, even though the two values are the same, but we would always store it as the simplest form. Now that's an implementation choice to make, but that's what we choose to do. And 0 is represented always as 0 over 1, because it's just to have, in order to have it in a standard form. One nice thing about that is it means when we compare two fractions, it means that if the fractions have the same value, they're going to have the same exact numerator and denominator, because we always represent it in its standard simplest form. Okay, so how do we enforce that? How do we guarantee that? Well, part of that is that if we have class invariance, then it's the job of the public interface of that class to make sure that those invariants are always true. When the class starts out in this valid state, where all these invariants are true, when you call a public method, then when you return from that public method, those invariants should also be true. There's no way for the user of that class going through the public interface of it to break those invariants, because that's the way we've designed our public interface. So the first thing we do is in the constructors, we ensure that we construct the object so that it's initially in a valid state. So we have two constructors for the fraction class. The first one starts on line 11, and it initializes a fraction with the default value of 0. So we put 0 in the numerator and 1 in the denominator. The more complicated constructor starts on line 18, and here we can construct a fraction with a arbitrary numerator and a denominator, but we manipulate those values to ensure that we end up with a valid fraction according to our rules. So if the denominator is greater than 0, all is good. We just store the numerator and the denominator. But if the denominator is less than 0, then we negate both the numerator and the denominator. So we have the same value, but in the standard form where the denominator is greater than 0. And finally, if the denominator is 0, then it's not a valid fraction. It's not defined, so we throw an exception. Then once we've checked that invariant, then we want to reduce it to its standard form, or to reduce it to its simplest form. So if we have a non-zero fraction where the numerator is not 0, then we get the greatest common factor of the numerator and the denominator, and we divide both the numerator and denominator by that factor. And that way we get the fraction in its simplest form. So for example, if we have 2/4, 2 divides evenly into both 2 and 4, and so we would divide both the numerator and the denominator by the 2 to get 1/2. Now, as part of that, we have a method here that we call on line 40 called greatest common factor. That is a private method of this class. So I'm going to go ahead and jump to that so we can see what it looks like. Go to definition, and we see that we have a whole algorithm that we use in order to, so result is going to the variable result on line 54 is the value we're going to return. That is going to be the greatest common factor. We start by factoring out all the 2's. So as many times as we can divide 2 into both numbers, we'll divide them by 2 and we'll multiply the result by 2. And likewise for 3, 5, 7, and so on until we get to the point where we can't factor out any more numbers from both. And then we have to check for the case where one number is divisible by the other. So that's our algorithm for greatest common factor, but you can see that it's private. It's a private static method because it's just part of our internal implementation. You don't have to actually call this method to use the fraction. It's just part of how the fraction class itself ensures that it is in its standard form. And we'll see that that method is used elsewhere as well. Okay, so that's the constructors. The constructor ensures that we're in a valid state to begin with. Now we have the numerator and denominator properties. These are defined as auto properties, what are called auto properties in C#, which means we haven't actually written get and set methods. We just wrote get semicolon, and that means that the property has a getter, and the compiler just generates the getter for us. There's a hidden field that the compiler creates under the hood, but really it behaves just like a variable, essentially, like a field, like a member variable. But these properties only have getters, no setters. That means that you can only set them in the constructor. Once the constructor returns, these values are read-only. So this is our way for this class of guaranteeing that the user of the class going through its public interface cannot violate our our rules, our internal state. It can't put the fraction in an invalid state according to the invariance that we've defined. Because once the constructor has set the numerator and denominator to be valid values, there's no way to change them. They'll stay the same forever. You can create a new fraction, or you can assign the entire fraction to a new fraction, but that fraction has also been constructed to be valid. So you can never end up in a state where the fraction is invalid. We also have some other public methods. We have toString. That's just a way of allowing the fraction to be converted to a string. So we can, call console.writeLine or string.format or what have you, and it will be formatted. We have, and this is an override because we override a method this is one of the methods that's inherited from the common base class object, which everything is derived from. Or in the case of struct, I guess it's really coming from value type. Then there's an equals method that is similarly also inherited from object, so we override that to allow fractions to be compared for whether they're equal or not. Then if you implement object equals, you should also implement object get hashcode. This allows you to store, to use the fraction as the key in a hash table or something. And we've defined just a way of computing a hash code by multiplying the numerator by a large prime number and adding the denominator. You can do it different ways, but it just allows you to have two different fractions are likely to have different integers for the hash code. They don't have to be, you can have hash collisions, that's okay, but as long as it's not that likely to happen, you're okay. Finally, as I mentioned earlier, what do you expect to be able to do with a fraction? Well, there are kinds of numbers, essentially. You should be able to do basic math operations on them. You should be able to multiply and divide and add and subtract them. So part of the public interface for a fraction is to have overloaded operators for multiplication, division, addition, and subtraction. And each of these is implemented by constructing a new fraction. So for multiplication, we just multiply the numerators together, multiply the denominators together, and then we construct a new fraction by saying new fraction. That will invoke the constructor, which will put the fraction in a valid state. So it'll end up reducing it to its standard form that we expect. And again, we go through the constructor for division. Division is exactly the same as multiplication, except that we multiply the first fraction by the reciprocal of the second fraction. So we take the numerator of a and multiply it by the denominator of b, and take the denominator of a and multiply it by the numerator of b. Okay, so those are public because it makes sense for these basic math operations to be it's part of the abstraction that we're trying to represent. So it's part of the interface. Now for plus and minus operators, we again make those public. We expect to be able to add and subtract them. But notice the implementation is calling an add method. That add method begins on line 100, and that is a private static method. And the reason that method is private because it's really just a way of us simplifying the implementation. So rather than having to write the same code twice, because addition and subtraction are very similar, we write it once, we put it in a method, and then we invoke that method from our plus and minus operators. When we subtract, all we're doing is we're negating the numerator of the second fraction. So we're adding the negative of the second fraction to the first fraction. But we then, in both cases, we invoke this add method to compute the result. And that add method is going to do the algorithm that we expect for adding fractions, finding the least common denominator, multiplying the numerators by the, multiplying both the multiplying the numerators so that we end up with two fractions with the same denominator, and then we can add the numerators, and then we can construct a new fraction. And of course, again, we're going through the constructors. The constructor will reduce the resulting fraction to its standard form. Okay, but by making this method private, that private method exists because it allows us to simplify our implementation. It's useful within our internal implementation, but it doesn't need to be visible to the user of the class because the user of the class is just going to use the plus and minus operators. That's how they will add and subtract fractions. And again, we have comparison operators. We can compare for equality by calling the equals method, compare for inequality by using the operators, and these all just delegate to a compare to method. Now the compare to method is public. The only reason that's public is because that method is part of the interface, the iComparable interface that we that we derived from, that we implement. And that is useful to have in a public API because by implementing that interface, it allows fractions to be sorted, for example. You can you can have an array of fractions or put it in a sorted dictionary or something like that. You can have an array of fractions and then sort it or put it in a sorted dictionary or things like that. Any case where you want to be able to sort things, implementing that interface is useful. But the underlying how we implement that compared to method, again, we have to find the least common multiple. So we're calling these private methods to do that. So these are methods that are only there only there to support our internal implementation, but all that underlying complexity of how we compute that stuff, that doesn't need to be part of the public interface. Having seen the implementation of the fraction type, fraction struct, let's take a look now at how it looks from the user's point of view. So the point of view of somebody using this type. So in this case, we have a main function starting on line 15. That's the entry point of the program. So this is just some test code. And in the main function, we just instantiate a bunch of fraction objects. So line 17, we have 1/2 and 1/2. Line 18, 1/2 and 1/3, and so on. And each of these pairs of fractions we then pass to the test method on line 3. So here we have the two fractions, which are in this context named a and b. And on line 5, we call console write line to write, a times b gives us the actual product of a and b. So this is using string interpolation. So the $ quotation mark syntax in C# means that inside that string, anything in curly braces is an expression. That expression gets evaluated and inserted in place of the curly braces. So in that line 5, for example, we have curly braces a. We'll take the fraction a, convert that to a string, which happens by invoking our toString method that we implemented in the fraction class. And then that gets inserted in place of the curly braces a. Then we say that times curly braces b, so the b fraction converted to a string. And then inside the last curly braces, we actually take a times b. So we're invoking the operator, the multiplication operator of our fractions. So we get a times b will return another fraction that's the product of a and b. That gets converted to a string and inserted in place of that. And then we do the same thing for division, addition, subtraction, the equality comparison, and the less than comparison. So if we run this, then we get, here's the output. Oops. So so line 5, so the very first line corresponds to the console write line call from line 5, and this is in the first call with the fractions being 1/2 and 1/2. So we have 1/2 times 1/2 equals 1/4, and then we have 1/2 divided by 1/2 is equal to 1, which is all as you'd expect, and so on. So this kind of gives you an idea of how the way we designed the public interface, the set of public methods and properties and operators and so on for this fraction allows us to use a fraction in much the same way we'd use a built-in type like an integer or a float or whatever, because we created the appropriate abstractions to make this class usable. But to use the fraction class, we don't have to know any of the inner workings of, for example, computing least common denominator or greatest common denominator in order to add them. We just say a plus b, and we get the sum of a and b. Okay, so having looked at an example, let's now consider some general guidelines for how you encapsulate your implementation in C# classes. Well, one of them concerns fields and properties. It is generally recommended if you're writing a class that you're trying to encapsulate the internal details, you should avoid creating public fields. And the reason for that is, well, first of all, it's good to understand what a field is. A field is really just a variable that is part of your class. It doesn't have any kind of code or it doesn't have any logic that restricts how you access the variable. You just set it or get it just like you would any other variable. And because of that, there's no way to enforce your invariance. There's no way to stop, if you have a public field, there's no way to stop the users of your class from setting that field to any value it wants. So there's no way to enforce internal consistency, for example. For that reason, you can encapsulate a field using a property. So in the example on the right-hand side here, we have a private field called m underscore name, and then we've encapsulated that using a public property called name. And the syntax used here, we have the property is declared to be public, we have the type and the name of the property, and then inside the curly braces we have the get and set methods. These are kind of special methods. They don't have any parameters. They have the special names get and set. Get just returns the value of the property, so anytime you reference the property, like on the right-hand side of an expression or whatever, anytime you're getting that property, the get method is invoked to return the value. Anytime you're setting the property, then the set method is invoked to set the value. And within the set method, there's this special parameter called value that's an implied parameter, and that's whatever the value is you're setting it to. So here the get and set methods are just trivial methods. The get method just returns the field, and the set method just sets the field. So you might reasonably ask, well, what possible value does this add over just making the field public in the first place? Well, potentially the advantage of having a property here is that we could add validation to this. In the set method, we could do some extra checking to make sure that the value is correct, that it abides by whatever rules we need in order to ensure that our class is in a consistent state. Furthermore, we can have different accessibility, different access control for the getter and the setter. You could have either the getter or the setter can be given more restrictive access than the property itself. So you could have a public property in which the set method, in which the setter is private, and that way only code within your class can set the field, but the users of your class can get the field. Furthermore, you can omit the setter entirely, in which case you have a read-only field. It only has a getter. The setting, and we saw that in the fraction class, that we had the read-only fields, and that means that the property can only be set during construction by the constructor, and after that it doesn't change. And since, of course, the constructor is part of the class, part of your implementation, it means that you're controlling what the value of that property is when you first initialize the object. So that's where the field potentially gives you that greater control over to ensure that or rather having a property gives you greater control to ensure proper encapsulation. However, in the case of a trivial property like this, where we don't do any of that validation, we just return the field and set the field, it seems like a lot of extra boilerplate code to write just for the theoretical advantage of being able to add validation later. For that reason, C# has what are called auto properties. It just makes it easier to add a property so that you're not tempted to add a field, in cases where it's just a trivial property that just stores a value. So on the right-hand side here, we have a equivalent property to the one we had before. So it has type string, it's called name, and then inside we have the get and the set methods, but instead of having curly braces, we just say get semicolon. That means that this is an auto-generated get method. The compiler generates a get method for us, and likewise for set. There is a implied, a hidden field that backs this property, because the data has to be stored somewhere. But the compiler just generates that field for us. We don't even really see the field. It's just we can only access it through the property. So this is really equivalent to the example on the last page. And you again might ask, well, why do this rather than just having a public field? It seems like the same thing. But it is still better than a field because, again, for one thing, we can make the setter private, or we can omit the set to have a read-only property, which is what we did, if you recall, in the fraction class. We had a read-only numerator and a read-only denominator, so they just had a get but no set. That's something you wouldn't be able to do with a field. But on top of that, by having a property, even a trivial property like this, even an auto property, it preserves your option of changing it later without breaking the interface. So we could later decide, well, during this set, I want to actually do some validation. So we would change this from an auto property to a property with an explicit field and with explicit code that we write to do the getting and setting. And at that point, we have the option to do that extra validation. From the caller's point of view, from the user of your class point of view, it's exactly the same. We're not breaking any assumptions that they make. They don't know whether it's an auto field or a or a excuse me, an auto property or a property that you've written yourself. So it preserves you the implementation flexibility to change the internal implementation later. Whereas a field doesn't have any internal implementation. It is what it is. If you change the field to a property, you are changing the interface. So in the first property example we showed, where we had an explicit field, we had a field initializer in the class alongside, at the same point where we declared the field, we specified its initial value. How would we initialize an auto property where we don't have an explicit field? Well, there are two ways. One is to do so to set its value in the constructor, as shown in the top left. And the other value is to use the property initialization syntax shown on the bottom right. So just after the property definition, after the closing curly brace of the property definition, you can specify an initializer there to set the initial value of that property. Both of these are possible, by the way, even if the field, or even if the property rather, is read-only, if it has a getter but no setter, because you're still allowed to set the property from the constructor, or you're not to initialize the property, you're just not allowed to change it thereafter. As long as we're talking about properties, so far we've just discussed properties that are backed by fields, or that encapsulate fields, even if those fields are hidden in the case of auto properties. But you can also have properties that just compute values on the fly. So to the user of the class, it looks like any other property, but in the implementation, there's no field. You compute the value of the property from something else. So we have three examples on the right here. First of all, let's say we have an age property. Maybe we have a class that contains information about a person, or like an employee or a student or something like that. Well, it wouldn't necessarily make sense, it probably wouldn't make sense to have a field that represents the age, because the age changes over time. You wouldn't want to have to keep updating that field as the person ages. Instead, it makes more sense to store the birth date. So you could have a birth date field or a birth date property, but it's still convenient to have an age property that you can get if you just want to know how many years old somebody is. So to implement that age property, instead of storing another field to store the age, you can simply compute the age on the fly from the birth date, as is shown in the code there, code snippet. To take another example, maybe inside your class definition you have a list of something, a list of item, as in the example shown here. So, and you want to have a public property called item count. Well, it doesn't really make sense to have an item count field, because the list already knows how many items it has. So the item count property can simply return the count from the list. So that's an example where we're just kind of forwarding the call to another object that has the count. Maybe we don't want to expose our list of items, but we do want to be able to tell the user of our class how many items there are. By the way, there's just a little bit of interesting syntax here, because the item count, in this case, the item count read-only property doesn't really look like the other properties we've seen so far, because it uses this lambda syntax, that little arrow with the equal sign, right? Equal sign greater than sign. That's the lambda symbol, and that can be used if a lambda method or lambda function is one where the entire function can be just a single expression. So you don't have to put in a curly brace and have a return statement. You can just use that arrow operator and have that single expression, and the return value of the function is simply the value of that expression. So for a read-only property, you can have the entire property just be on one line like that with the lambda expression. A slight variation on that is, that's A. A slight variation on that is B, which is really equivalent, but in this case we're using more the regular property syntax, where we have the property with curly braces, and then we have a getter where we have the named, the special get method, the property accessor method called get, but the get method uses the lambda syntax. So instead of putting curly braces and a return statement, we can just use the lambda syntax for the get method. Any method can work this way, where you have the lambda syntax. And finally, for item C, we have the syntax we're used to from other examples here, where the method is a full-blown method with curly braces and a return statement. All right, we've talked about fields and properties quite a bit. What about methods? Well, there's no hard and fast rule for methods like there is for fields. So fields are kind of special because they don't have any intelligence in them. They don't have any ability to ensure the internal integrity of a class or to allow you to add any kind of flexibility. None of that really applies to either methods or properties. So methods may be either public or private. It just depends on what their purpose is. So again, as you're describing the observable behavior or the public interface of your object, of your class or struct, then you have to decide what things make sense to expose to the users, what things they need in order to use your type, and what things are just part of your internal implementation. In the example shown here, this comes from our fraction class. We again see the add method, and that method is private because it's really just part of our internal implementation. It makes sense to have this method because it allows us to avoid writing the same code twice when we write the plus and minus operators. So factoring that into a separate method makes sense, but it makes sense for that method to be private because the public interface only needs to include the plus and minus operators. It would be kind of redundant to have a named add method also as part of its public interface. So that's an example of where private methods make sense. So to summarize, we've learned how creating well-defined interfaces between different pieces of software is a key part of doing good software design. It allows you to manage complexity so you don't have to have every little detail of every part of a program in your head at once. Each chunk of code, each object, each class, etc., has its own internal details, but it also has, and then it has an interface, which is the set of abstractions that the user of that code needs to worry about, needs to understand. So the interface exposes the observable behavior of the class, the stuff that's visible to the user of the class, and it should be clear and well-defined and not unnecessarily complicated. The implementation of that interface is how that is represented under the hood as just the raw data and whatever operations you need to perform in that data. That's the implementation. Encapsulation is the idea that you don't want the user of your class to be concerned with that raw data and those low-level operations in the data. You want to encapsulate those by having a set of methods and so on that perform those operations in a way that and exposes higher-level concepts on top of them. So the encapsulation is defining those higher level concepts in terms of that lower level of representation that you have inside. Information hiding, which is the public and private that we've been talking about, is how we enforce encapsulation by ensuring that only the internal implementation of the class sees that raw low-level representation, and the users of the class only see the public abstractions that you have made part of your interface. In C#, the public and private keywords are how you do information hiding. Public is for the interface, the observable behavior, and private is for the underlying implementation. And there are some general guidelines, namely that fields should pretty much always be private because they don't really have they don't have any facility for enforcing boundaries. You can't control how a field is modified if it's public. But properties, methods, and so on may either be public or private, depending on whether how their purpose aligns with what you're trying to do. If their purpose is just to simplify your implementation, then they're private. If their purpose is to expose functionality that's part of your interface, then they should be public. So I hope that the concepts described in this video are helpful to you in writing software that is better organized and easier to maintain. Thank you for watching.